Hello. Hello, Mr. Aaron, Mr. Ryan. How are you today?
Show.
Okay, so remember a few months or maybe several months ago, we talked about a game, jump game, right? An array. So each number, you are at position
I don't
0.
remember anything about the jump game.
Look, this number means that the furthest distance you can jump. Look, 2, you can jump to 1, 2. Right?
Yes.
1, you can jump 1. A few months ago, we talked about another similar problem, which you can jump backwards. Right? But now, today, with this problem is a little bit simple. So you are at the beginning, you are here.
Yes.
That's you. Right?
I'm naked.
Not naked, okay, with some dress, okay. Okay. So 2, it means that the next one, the furthest distance you can jump is here, right? Yeah? 1, 2.
Hey guys,
okay?
I'm going to Mayfield.
Okay.
Yeah.
So now you're here. So now you can jump 1 to the front. So you're here. And then you can jump 1 to the front. So it's here. So the question becomes whether you can jump from the beginning to the end. Got it? Yeah? Does it make sense? Okay, this is not a drawing lesson. Come on. That's not a drawing lesson. What are you drawing, Pokemon? What's that? A cat. Cat. Okay, what's this? Oh, that's a nice cute cat. So, okay, I repeat my question, okay? So you're at the beginning.
Yes.
And the number means that the maximum distance you can jump forward only. So 2 means that you can jump forward to here, right? Yeah?
Yes.
1 means you can jump here. And 1 you can jump here. So you can jump from
What if you
beginning
can't
to...
reach the end properly?
You tell me false.
Oh.
If you can jump, you tell me true. If you can't jump,
Yes.
tell me false. Got it?
I tell you true.
Okay, another question. Another here. Look. 2, 1, 1, 0, 0, 4. Can you jump from the beginning to the end?
2, 1.
Can you jump?
No.
No. Oh,
Because
yeah.
there's a 0.
Yeah, at the 0, you can't. It means you stay still, right? You can't jump forward, right? Okay, so look 2, maximum here. 1 here. You can only jump the furthest distance. You can jump at this point. And now you're stuck with here because you can't jump forward, right? Got it?
Yes.
Any idea we are solving this problem? I know there are quite a lot of algorithms we can solve. We can, what kind of algorithm do we think? Because look, this is kind of like what kind of algorithms? The search, right? So what kind of search we can do? What kind of search we can do?
We can do
Previously we talked.
practice search.
Yeah, remember a few months ago, the problem becomes that at 3 you can jump forward or backward, right? 2 directions. And then at that time we use the depth search, breadth search, right? This is the simple version of that. So obviously we can still use the depth search, or we can still use the breadth search, right? Right? Yeah? Yeah, make sense? Ryan, you're busy. Are you finished yet? What's this?
That's an electrode.
And what's this?
Snorlax.
What's this? Turtle.
Wheezing.
Okay, I have no idea what this draws. Okay, so depth search, breadth search, yeah? Depth search, in this case, look, how can we depth search? How can we depth search?
We can just
So we
just can move along.
something. Look at here, right? I'm at here too, right? Right? So the next one I can jump is 3 and 1, right? Yeah. So I can jump to the 3, or I can jump to the 1, right? If I jump to the 3, I can jump to the 1, 1, 4, right? 1, 1, 4, right? If I jump to 1, I can jump to 1, right? Right? Got it? Am I right? Do you get this? We expand trees, search trees via depth search. Right? With depth search. Look, and the 1, next one and 1. Okay. So do you notice there's a problem here? What is that? There's some places we have visited, many times, right? Got it? Yeah. And we can do one simple solutions to make sure we don't calculate it over and over again. What keyword is that? What keyword?
Dynamic programming.
Dynamic programming, and especially we use the keyword add.
Cache.
We're done. Cache. To cache this
Oh,
need
yeah.
there. Yeah. Remember cache.
I only drew a cat.
Cache. Okay. Cache. Okay. Okay. Let's try this depth search. Okay. If we don't put a cache, it becomes like a backtracking, right? We jump backtracking. We go So we are the current position. Then we start to jump as furthest as possible along this way. And then if we can't jump, we just backtracking to the previous one. And if we put a cache, right? Look, why do we need to put a cache? Look, three here. The next one will be 1, 1, right? These two, yeah. Look, 2, 1. So this one, look, this one. Alright, look, this one here, right? Is the same as this one, right? So what does it mean? So this subtree is the same as this subtree. So that's a duplication, right? If we don't put a cache, the complexity will be exponential because we're over calculating, repeatedly calculating the same thing over and over again. That's why we put a cache, right? Put a cache, that means that it's also a kind of top-down dynamic programming, right? Top-down, yeah, top-down dynamic programming. It's also we can implement with recursion, with cache, which is called minimization. Yeah, okay.
Yeah.
Okay. Let's implement this first. Okay. Preferred search we skip it today, but it's quite simple. Yeah. So I just give you this idea again. Okay. 2. I can go to 3 and 1. I travel over 3 and 1. Right. 3. I can travel 1, 1, 4, right? You see, I visited this level by level, right? Yeah, level by level. Okay, so let's do it. Okay, I need these to erase.
DFS. Ow.
Okay.
I haven't drew finished.
I let you draw.
Hey,
I let
why
you draw.
is it wet?
Yeah, because I just can't. Okay, can you go back to there?
I only drew a cat.
I give you the chance to draw at the end of lesson. Okay, you will be very good. Okay.
And Ryan drew a load of Pokemon.
So what is
Ryan drew the
that?
cat.
What is that going to do now? Depth of search, yeah. Implement the depth of search, yeah. Oh my God, I need a tissue because it's so dry. Okay, excuse me a second. Okay, I need a.
Excuse us. And then.
No. It's too noisy. Come on, guys. Too noisy. Okay. So Dad is going to draw the no. Yeah, that's it.
No.
Oh, sorry. Can you sit there, please?
Super owl.
Sit there. Okay.
Super owl.
Can you not touch the camera? It's shaking. People will feel dizzy. Okay.
I didn't shake the camera.
Define.
Ryan did.
Define. Okay, right. I probably need a define. Oh, I think I lost it. So define depth of search. Yeah, define depth of search.
You have my smiley face.
Define depth of search. Okay, depth of search. So look at actually let's jump. Let's put it a jump here. Jump.
Earthquake.
Jump. Okay. What you doing here?
Earthquake.
Okay, jump. Let's say we have numbers here.
Okay,
Okay, so now first of all we know that this there's how many numbers in the length in the numbers, right? And then we do a depth of search. DFS. Now we are at current position, right? So I will start filling this function. Look, Eric. And all I need to do is return DFS 0, yeah, because we start at the 0, right? Right? Yeah? So now look what? What should we do with the depth of search? So at the beginning, what should we do? What should we do?
we should do.
So look, if this current position is bigger or equal the n, right? So it means that we know it's already, we can reach the end, right? Eric? Yeah, we can reach the end. So we return what? Come on, we can reach the end.
We return.
Come on, the binary. Yes or no? We can reach the end.
Yes.
Yeah, true, right? Now we are at current, right? So we can do this for I in range.
Babe.
Range what? Range what? We start from 1 and to the current Lamb's current, right? Lamb's current plus 1, right? Because we can jump from current position we can jump 1 step forward, two steps forward until numb's current position, right? And then now look what. But obviously, if this is over the boundary, we need to restrict this and to the boundary. So we will replace this with mean n and this number, right? And now we can just say if dfs I, right, plus nums. Alright, look, this is a dfs. If we can from this current position, don't work here and there. This is the current position, and
Dude.
actually no, actually it's current because we are at current, right? We are at current. Okay, we are at current, and if we can jump this step, and we can jump to the end, and we return what? Return what? Come on.
Return.
We can jump to the end by 2, and then otherwise, if we can't find it, return what? This is the depth of search, yeah? Okay, so what's the time complexity of this implementation? What's the time complexity of this implementation? What's the time complexity?
The time complexity.
Yeah, what's the time complexity of this implementation? Come on. Backtracking, actually. This is the backtracking, not Come on, remember, look. Look, I'm here. I'm here. Look. This position, yeah? Look. 1, 1, 1. Look, the worst case.
Yeah.
The worst case is all 1, right?
Yeah.
So at here, I can jump to this. At here, I can jump to this, right?
Yeah.
Or 2. Maybe 2 is better. Look, 1, 2, 2. From here, I can jump to this point and this point, right? From here, I can jump here and then here, right? From here, I can jump here and here, right? So every time I jump, look, this is jumping
Like what?
2 steps. Oh, what? Come on, don't guess. What? What's the time complexity?
When?
What? Look, every time, look here, I can jump here and here, and here I can jump here and here. Remember, every time I can expand into 2. What's the time complexity?
Square.
No, really, no.
Again.
No, no, look, you need to think, not
I
guessing.
am thinking.
Okay.
Again.
I'm saying that at each position I can expand to 2, and each position I can expand to 2. So how many of the ways of doing that? How many ways of doing that? There are n here.
Yeah.
So look, each one I can expand. Look, each one I can expand to 2. Yeah. So how many of these are there? How many of these are there? It's exponential. What can you think of exponential one?
It goes forever.
Oh, that 2 to the power of what? 2 to the power of 1. Come on.
Yeah.
Yeah, understand. So that's bad. We want to avoid. Why is that? I told you before. Look, because these subtrees we calculating over and over again. Look, 2 to the 2 here, right?
Yeah.
And then here from look.
Yeah.
2. Can you look at me? If you don't look at me, you don't understand. Look, 2. I can jump from here and here, and 2. I can jump here and here. Look at these 2. Look at these 2. If I calculate from this point, I jump here. But again, from this point, I can jump here. The second time, I don't need to calculate it again. It's like Fibonacci number, right? It's like Fibonacci number. F5 equals F4 plus F3, right? Look, F4 equals F4, F3 plus F2. You see the problem? F3 equals F2 plus F1. You see the problem? You see the problem? F3, repeated calculating, right? F2, yeah? So if we don't put a cache in a Fibonacci number, the time complexity is exponential. It's the same here, backtracking. So all we do, how do we fix it?
Dynamic programming.
The easiest way, dynamic programming. How do we fix it? Remember the values. Top down. Remember the values. How do we remember the values? Brian has said it before. What's the keyword?
Cache.
Cache. Yeah, cache. We remember it. So every current, if you visited it, we store it. So that it doesn't calculate it again. But who can use this value? Who wants to use the value? That could be there could be n values in front of it, needs to use this value. So let overall this time complexity is O(n) square, okay? Okay,
We said O(n) square.
without the cache. With cache is O(n) square. Without the cache is exponential, okay?
Oh.
I understand this is a bit too difficult to you. So now I'm not going to ask you any complexity, time complexity. Yeah? If you don't understand, that's fine. This is depth search, right? How about we can solve it? This is top-down dynamic programming. We can solve it with bottom-up dynamic programming, right? Yeah?
Yes.
Bottom-up. Remember what's bottom-up? Bottom-up. Yeah? Bottom-up. Remember. Look, Fibonacci number. Every time we said about top-down and bottom-up, you can always remind yourself with the Fibonacci number because that's the easiest problem you can think of using the top-down and bottom-up dynamic programming, right? Look, F3 equals, look, Fn, right, equals Fn minus 1 plus Fn minus 2, right? This is a top-down, this is a Fibonacci number, right?
Yeah.
Top-down, you calculate Fn and you need to calculate Fn minus 1 minus 2, and then we use the cache. This is expanding to the tree, right? Look, 3, 2, 1, and then 1, 0, right? So top-down is this way. You want to calculate F3. You want to calculate F3, you need to calculate F2 and F1. If you calculate F2, you need to calculate F1 and 0, right? Bottom-up is this way around. We calculate F0, F1, F2, F3. So, right? We calculate this way. So we start with F0, F1, and F2 this way. So this is bottom-up, right? The same. So look, this DFS current, this is the function to tell if we can visit it, if we can jump from the current to the end, right? So we can create a function, an array, and to do this bottom up to fill in the values, right? Let's do this. Probably need a better eraser. So let's say dp equals, at the beginning they can't be reached from the end. We set it to false, right? And initial state is false, right? False times n, right? But we at the last point, right? At the last location, it's true, right? Actually, it's true because you are already at the last location, so you know dp minus 1 is true. So what's dp mean? dp is the dp0 means that if we can jump from the position 0 to the end, right? That's what it means. So and the answer of this question becomes return dp0, right? dp0. Okay?
Yeah.
Okay, so then we can start filling the values from the right hand side to the left, bottom up, right? So we can do this. For I in range, start from the last value, which is n minus 2. Because n minus 1 we already know it's true, right? N minus 2 to 0 every time I decrement 1. Look, this is to 0, yeah? Excluding the last value, which is minus 1, okay? And then this is a step. And then now we want to calculate the reach. What's the reach? The first is you can jump, which is the minimum of n minus 1. And then I is the nums I plus, because you are at I position, and then you can jump from I to nums I, right? Do we need to minus 1 here? Actually, I'm not quite sure. Let me check. I think, yeah, you need to minus 1 because, yeah, minus 1 is the last index. I minus nums I, right? Okay. Okay, so now, look, this is the furthest you can reach. And then we can start from what? For j in range, we start from I plus 1, right? To reach plus 1. And if dpj can reach, then dpi also can reach. Yeah, this is very important, right?
Very important.
Look, Eric. Here, I'm here at this position. If dpj, because I know this is dpj, this is dpj here, dpi is here. I know I can jump to j. So if dpj can reach to the end, then dpi also can reach to the end. Am I right? Does it make sense? You sure? Does it make sense? I plus 1 reach plus 1. Yes, exactly. So Eric, look, dpj means that if we are standing at j, can we reach to the end? Because we know dpi can jump to dpj, right? We know I can jump to j. So if dpj is true, what does it mean? dpi is what? It's true, right? So that's what it means. And then we return dp0. What's the time complexity for this one?
Hey, I thought you said they're not going to answer any other.
Just guess. There are 2 false. Bonus. 2 false.
ON
square.
Wire down. Easy. Easy peasy. What's the space complexity?
ODP.
Oh, and easy peasy. Okay. So that's the bottom up dynamic programming. Okay, because we are bottoming up. The bottom is on the dpn, right? dpn, not dp0. So this is kind of like a tree, growing reversely. So dpj is dpn minus 1 is the answer we want to. dp0 is the answer we want to know, and then we grow it. We calculating. We are not calculating from dp0. We calculating from the reverse. dpj, dpn minus 1, dpn minus 2. dpn minus 3 until we reach the dp0. Okay, that's the bottom up. But top down, right? Remember, we return dfs 0, right? dfs 0. So it's this way. Top down. Bottom up is this way, right? Got it? Because we start filling this dp minus 1. What's dp minus 1 mean? Just very simple. What's dp minus 1?
dp minus 1 means the first.
Cash.
First or last? Come on.
Last.
dp0 is the first, yeah?
I keep on forgetting dp minus
0, look at 0 means the first one. Computer, the array index start with the first one, right?
Yeah.
Minus 1, the other side, yeah, minus 1. Minus 2, the second to the last, right? Etc. Okay, so now, can we do better? Because all the previous two, depth search, backtracking, top-down dynamic programming, yeah, recursion with the memoization, and this bottom-up dynamic programming is all n square, right? In the worst case, O n square, and we use this memoization to remember the values that so that we don't calculate it over and over again. But if you look at this problem, it's actually we can go through this greedy. What does it mean? Look, look. I have this max reach. We can reach. Okay, max reach variable. At the beginning, we updated 0. So now let's do this problem. 3, 1, 0, 2, 4, 1, 5. Okay? Can we reach to the end? Can we reach to the end? Yes or no?
1, 2, 3.
Okay.
1, 2, 1. Yeah.
We can reach, yeah?
Yeah.
Yeah. And how can we do that? Look, 3. How far we can reach?
After 2.
1, 2, 3. Here, right? So max reach is here.
We don't
Okay.
want to reach on 1 or 0.
Yeah, okay, that's right. We update this max reach, yeah? Here, max reach. We don't need to update max reach because it's, look, 1 is less than max reach, yeah? We ignore it. 0, ignore it, right? I'll go through here. 2, max reach updated because look, you can go through to the here, right? Yeah?
And then you could go.
And then go for, yeah, max reach. Update the max reach, right? Yeah, max reach here, I can go to here. And then 1, we don't update the max reach. And here, look, when we go to the end, we just check if max reach can reach the end. That's it, simple. Yeah?
What if, oh,
Do you get it? And let's find an example that we can't
So if
jump.
reach to an end,
Yeah.
it's true.
Yeah, exactly. Oh, well done. Look, if let's see another example. So, look, 3, 0, 0, 0, 1, 100, 2. Can we reach it?
no.
Okay, 3. Max reach to here, right? Yeah? 0, we don't update it. 0, or maybe we change it here to 1 as well. No, we don't update it. 0, we don't update it, right? 1, we don't update it because because max reach is smaller than than this point, so we don't update it, right? 100 we don't update it, 200 update it. So the max reach is less than n, so we don't update it, right? So there are two things we need to check. One is when we update it, we need to be sure that the current position is less or equal than max reach, right? If it's bigger than max reach, then we don't update it because we can't jump from the beginning to this point. So there's no way to update the max reach. Am I right? Yeah?
Yeah.
So what we do is going through this one time. What's the time complexity?
O-N.
O1, we're done, yeah? You see? Just one time, O1, right? What's the space complexity? Do we use any
O-1.
O1? Because we only use one variable, it is not linear to the program
What about
scale.
the max reach thing?
Yeah, max reach, yeah, we are using a variable, but it's just one variable. It's not linear. It's not an array that affected by n, right? It's not linear, right? That's the difference. O1 constant doesn't mean it doesn't use any space. It means that you use constant number of space. It means that no matter how big is your array, how big is this, all I use is constant term, constant thing. It doesn't grow. If I need to allocate another array which is size of n, then that's O(n), right?
Yeah.
If you have a million items in an array, and I need to create another array which is a million, then that's O(n), right? Yeah, you see the problem, yeah? Okay, then let's write this. This is called greedy. You know what's greedy?
Because you want to get the biggest one, you want to
Yeah.
give it to yourself.
Greedy means that always you update it with the furthest, yeah? Okay. Define can jump.
Yeah, I got the biggest, and I'm gonna keep it to myself.
Okay, then let's say the reach n equals length num, right? Reach equals 0. I equals 0, the current position I, yeah? Look,
Yeah.
y I smaller than n, and also I is smaller than reach, right? Small or equal reach, right? Yeah, small or equal reach. Now what should we do? What should we do? Oh! What should we do? Huh? What should we do?
We shall
Update the reach, yeah? Reach equals what? Reach equals what?
Min.
Reach equals what? Look, we are at here. We are at this position. We want to update the reach. Reach equals max reach
Zero.
what?
Max.
I plus nums I, right? This is the furthest distance it can jump. And then what? I plus equals
1.
1 moves there. And return, how can we check if we can jump from the beginning to the end?
Reach.
Reach
And no.
bigger
Bigger.
equal n minus 1. The last incident is minus 1. Ah, got it?
Yeah.
Make sense? What's the time complexity? I just asked you, yeah? Can you answer it again?
O-N.
Okay, let me check if there's anything I missed.
Out.
Okay, missed out today. I think that's it. So to sum up, we have talked about this problem. How many solutions we have talked about?
3.
First one is depth first search without the minimization, which is called backtracking. Yeah, backtracking. So this complexity is a bit complex. It's O to n, right? Exponential. Just remember the Fibonacci number. It's quite similar.
Yeah.
Okay. And if we put a cache, depth first search with the cache, what do we call it? Top-down dynamic programming. Yeah. Top-down dynamic programming. Recursion with the minimization. Yeah. The time complexity is O n square, right? And then since we can do top down, sometimes most of the case we can do bottom up, yeah, easy. Bottom up. Dynamic programming, yeah, dynamic programming. We fill this array from the right hand side to the left hand side, right? So that's top down, bottom up is also O(n) square. Yeah, the space complexity for these two is also O(n) square, okay? And then now we talk about this greedy. Really, yeah? Because we can always update the furthest distance. Yeah. When we current position is smaller than reach, then we can update it until we check if the furthest distance is bigger or equal than the last index. This is the time complexity is O(n) and the space complexity is O(1), right? We also mentioned the breadth search. Breadth search, yeah. Breadth search is like this because It's like that, yeah. If we put a cache, can we put a cache on buffer search? Maybe, but it's too hard. We can use the minimization table, minimum.
Oh yeah.
Yeah, if we use the minimum, then the time complexity will be reduced to O(n) squared because so we have a flag like dpi means that if we can jump from I to the n, so we only calculate this once, right? But it may take other. How many times can in the words do we need to access this dpi? Is O(n) times, so O(n) times n, so it's O(n) squared. So this buffer search. Actually, depth search and buffer search is quite similar. It's just different ways of traversing the tree, right? Traversing the tree. Remember? Okay, 1, 2, 3, 4, 5, 6. What's the depth search in this case? This is 4. What's the depth search of this tree if we search this? 1, 2, 6, 3, 4, 5. What's the breadth search?
1, 2, 3, 6, 4, 5.
You see, just different ways of traversing it. The search, the domain, the search space is not. It's the same, right? You still need to search. You still need to search the entire tree, so it doesn't make a difference. It's just different order of traversing the tree. The most important thing is cache, because we don't want to calculate it again and again. And the most optimal solution for this problem is greedy, because we update. We just go through the array once and that's it. Okay, and that's it. We don't go through another time. So it's linear O(n). So which one is the best? Come on, I haven't asked you. Which one is the best?
Well, greedy.
Greedy, obviously. Okay, because it's less complexity. Well done today. Okay, good job.
Yeah.
Any questions so far? Any questions so far? Or you want to show people your drawing? That's it? Right, Eric? Ryan?
Aye.
Okay, should I wait for you to finish? You want to say hello, thank you, bye bye to people? What are you drawing? A kitty or a Pokemon? Pikachu, okay. Show us your drawing skills. Come on, that's it. You're taking so much time. Hurry up.
Just wait. Ta-da!
Well done. Okay, say bye bye to people.
Bye bye.
Bye bye.
Boom 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 boom.